Okay, so we're going to talk about how to find limits algebraically. And so we did a little discussion about limits when we were looking at graphs and seeing what a limit looks like on a graph. And I think that, just to sum up, if you remember, if we had a graph that was something like this, let's say that this is, 1, and this is, if I were going to look for, and this is f of x, if I were going to look for the limit as x approaches 0 of this function, well, since it's a continuous function, the way that I would do it is I would just look to see what the value is at that moment in time. So, and we would know that that was a 1 because it's approaching the 1 from both sides. We saw that if it was a hole, so if there was a hole here at 1, the limit as x approaches 1 in this picture, even though I have to jump over the hole, so this is a discontinuous graph. This one's continuous, right? So continuous functions, their limit is always the same as the function value at that given time. So whatever the function value is at 0, that would be the limit if the function's continuous at that moment in time. Well, this function is not continuous at that moment in time, so I have to find some other strategy. And since I'm looking at the picture, I can clearly see that the limit for this one would be a 2 because this graph is getting closer and closer to 2 on both sides, right? And we saw that the other kinds of things that could happen would be something like asymptotes. And this guy would not have a limit at 1. So if this were h of x, as x approaches 1 in this graph, the limit would be does not exist. Okay? So, and then, things like endpoints. That's also a place where you don't have a limit. So the limit here at 1 of q of x as x approaches 1 would be does not exist also because there's nothing happening over here, so you can't be approaching the same value from both sides. Okay, so we decided all that stuff was true. So this, we said, was a non-removable discontinuity because I can't redraw this map without the discontinuity. Or redraw this graph, I meant to say, not map. I can't redraw this graph without this discontinuity, without changing everything about who he is, right? You'd have to eliminate this asymptote, and then he would be a completely different picture. This guy, I can't eliminate this endpoint and add more graph, or it would in essence change everything that makes him who he is, right? But this guy, I could probably draw one that's almost identical where we just put a little makeup on this little freckle here and he would be the same guy, right? It would be just a little tiny cosmetic change to just fill in that hole. So this one would be called a removable discontinuity, we said. Okay, so these are the ones that we're going to be able to work with, and these are the ones that we're going to be able to work with in this algebraic methods that I'm going to be showing you. These other ones you'd have to find other ways, but I'm going to show you how to algebraically take care of this, okay? So let's take a look at the first one. So the first one that we're going to look at is easy. Let's say the limit as x approaches 1 of something like x squared plus 2x. All right, so there's a couple things you could do. We could just know what this looks like because we're not dingalings and we've worked with, quadratic functions a lot. This is an upward-facing parabola. You could probably very easily find the vertex and some points or whatever you needed if you wanted to graph it. But everybody knows basically that it's this picture. Okay, now where it is on the XY axis, I don't really know, and I don't really care. I do kind of know, but I don't care. So I'm not even going to bother to try to figure it out. Okay, so then I know that if this is a continuous function, then the way to find the limit is what we call by direct substitution. And the funny thing is that all limits are really, when we find them algebraically, boil down to direct substitution. The last step is always direct substitution. In this case, there's nothing else to do but direct substitution, so that's actually what we're going to do. So the limit as x approaches 1 is actually whatever the function value is at that moment in time. So it's 1 squared plus 2 times 1. So that's a 2, so that's a 3. So this limit, so whatever we are at 1 here, right, this would be a 3. So it wouldn't be that picture exactly, but, you know, so that's just saying that that function is going to be getting closer and closer and closer to 3. So direct substitution. So whenever the function doesn't have any problems, if there's no reason for me to not plug a 1 in there, then I'm going to do that, right? And that would also be true even if the graph is discontinuous, as long as it's not discontinuous at the point that I'm looking for. So if it was going to be 1 over x plus 2, well, this is a discontinuous graph. It actually has a non-removable discontinuity. It has an asymptote. But because the discontinuity happens at -2 and not at 1, I can actually use direct substitution to evaluate this one. So I'm going to do it the same way I did up here. The limit is going to be 1 plus 2, so the limit's going to be 1/3. Okay, so the first thing you should always check when you're doing these limits is to see if you could just plug the number into the function. If you can plug the number right into the function, then that's the limit, and you don't have to worry about it. All right? Now, some other ways that we should be thinking about these are finding a way to make it so that you can plug in the number that you're looking for. So we have limit as x approaches -3 of x squared plus x minus 6 over x plus 3. Okay. Now, I can't just stick a -3 into this function because that happens to be the moment of discontinuity, which means I'm not allowed to stick a -3 in there, right? And we actually, because we know a bit about rational functions, can tell whether this is a whole or an asymptote, right? Now, if it's an asymptote, it means that the limit doesn't exist. But if it's a whole, it means that I actually can find the limit. So what I'm going to do is I'm going to try to figure out if it's a whole or an asymptote. And how do you figure out if it's a whole? Well, remember when you did rational functions, you factored out the top and you factored out the bottom, and then you looked to see if any of those things would, you know, divide out to give you a 1 or cancel, in other words. So at the top, I'm thinking there's probably an x plus 3, and the other one is a what? X minus 2. All right, so now you can see here that the 3 is actually a whole. That moment of discontinuity is a whole and not an asymptote, which means there is a limit there because there are limits at wholes. So the limit of this guy is actually going to be the same as the limit of his twin. So this is that guy where we said, I don't know where I put that paper. So this is that guy that just has that little bit of cosmetic work on his face, right? He's just going to fill in that little hole, but in essence, they're going to be the exact same picture except for the hole. This is going to be a line with a hole in it, and the hole is going to happen at -3. So it's going to be continuous everywhere else. It's just going to make that little jump. And so the limit of this one and this one are actually going to be the same because they're the same picture, basically. Okay? And the only time that they're different is that one moment in time that I don't care about, because remember, limits don't care about what happens at -3. It only cares what happens on either side of -3. So this function can tell me what happens on either side of -3 because it can tell me what happens at -3. Now, if I put a -3 in here, it would be like finding the y value of the whole. And since the y value of the whole is going to tell me where this function is getting close to, then it will give me the limit of this function. So what I'm going to do is I'm just going to put in a -3 now that I am allowed to, because there's no reason I can't stick a -3 in here. So my limit is going to be a 6. No, I'm sorry. It's -3 minus 2. So it'd be a -5. I put multiply like a doofus. But here we go. So it's -5. All right? So that's my limit. So the first thing that we always check is, can you just plug it in as it is? If not, then you're going to look to see, is there some way to cancel out the thing that's causing the problem? Why can't I use direct substitution? So in this case, the reason why I couldn't just stick in a -3 was this guy. He was the troublemaker. So I had to find some way to get rid of him. In this case, it was easy. I just canceled him out after I factored, right? So that was a pretty simple. If it had been one that I couldn't cancel out, then I would just have to check to see if if it's the kind of discontinuity where they're both going up or they're both going down, and then I could talk about it in terms of infinity or negative infinity, something like that. Okay. All right, so let's look at another one. Let's do the limit as x approaches 0 of x plus 1 minus 1 over x. Okay, so this is a very common one. Sometimes there's different numbers or whatever, but this style of question is very common. So this one they often call, rationalizing, or, sometimes I think of it as using the conjugate. So sometimes the radical is on the bottom and sometimes the radical is on the top. But in this case, this is the thing that's causing the problem, right? This is the reason I can't put a 0. I could put a 0 in here and that would be fine. But this x is the reason why I can't just use direct substitution to find this limit. All right. So I need to find some way to cancel this x out, because that's really the only way to get it to disappear in a fraction, is to, divide it out. I can't divide it with this guy on the top right now because this guy on the top is inside of a grouping symbol, so I can't really get at him. So this is like a double grouping symbol. So in order to get this guy out of the grouping symbol, I know a lot of people always say, well, just multiply by the x plus 1, but the trouble is this top is a binomial. So if I multiply by just the x plus 1, the square root of x plus 1, and I, multiply it out, I'm going to end up with another. This is actually going to give me when I multiply with that, it's going to give me another radical. So what we're going to do here is the same thing you would do if you were rationalizing a fraction. And that's why oftentimes it's called the rationalizing technique. So how do you rationalize a fraction? Well, that's when we start to talk about our conjugates, right? So if you remember the conjugates, it's the same two terms, but the thing in the middle is different. So this one is a minus, this one is a plus. And why do I want that? Because everybody knows when you multiply a plus and a minus, a sum and a difference of the same things, that you're going to get a difference of squares, right? And so I'm going to get that difference of squares. That middle term is going to drop out and I'll have no radicals left on the top. I will have radicals on the bottom, but the point is I need to get an x out here. So on the top, I'm trying to get x multiplied with something so that I can cancel it with x multiplied with something on the bottom. Okay, so that's really my goal here. And hopefully I'll be able to accomplish that. So I'm going to write my limit symbol again because I haven't evaluated the limit yet. So I have to keep writing this until I actually take the limit. I'm just altering this expression inside. And of course, if I multiply by this over this, I'm multiplying by 1. So I'm not changing this expression. I'm just multiplying by 1 and making him look different. He's going to have the exact same value. So it's like changing 1/2 to 2/4, right? Okay, and remember, we're going to FOIL it out, but this is going to be -1 of that, +1 of that. That middle term disappears. So it's going to be x plus 1 minus 1 squared all over x. And don't forget that this guy is on the bottom. I know every once in a while I forget to write that down too. We're multiplying, when you multiply fractions, you're multiplying the top and the bottom. So sometimes people just ignore this and forget him. All right, now if we take a look at the top, again, I'm writing my limit symbol. X plus 1 minus, 1 squared is 1. So at the top, I just have an x. And isn't that nice? Now, since x is multiplied with this thing on the bottom, and x is actually by himself up at the top now I can cancel these out. And now I know for sure that this kind of discontinuity that's happening at this point is actually a hole and not an asymptote because it canceled out. Okay? So that's how I knew it was a hole before. That's how I know it's a hole this time. It cancels out. I know it's a hole, which means there is a limit. And I can find that limit now by using direct substitution. So what am I going to be looking for? I'm actually going to be looking for the limit of his twin, which happens to be this guy. And I'm just going to use my direct substitution. I'm going to 0 in everywhere I see x. So it's going to be, now I'm going to drop the limit symbol because I'm going to, as soon as I put the 0 in, I've evaluated the limit. So once I do the substitution, the limit symbol is gone. So I am evaluating the limit when I substitute. So I no longer need the limit symbol. But I needed it everywhere up until now. Okay, so when I put in the 0, I'm going to get square root of 0 plus 1 plus 1. So the square root of 1 is 1. So this is a 1 over 2. That's the limit of this guy. And you don't want to see? So let's take a look. Let's put in this function. So the square root of x plus 1 minus 1. Did I do it right? I think so. Divided by x. And let's look at the table. We'll look at the table first. So we're looking for numbers as they get close to 0. So I'm going to check on either side of 0. So I'm going to check 0 0.1, 0 0.001, 0 0.0001. And at some point, the calculator can't even tell the difference between 0 and my number. Okay, so 0.0, 0.0001, the calculators kind of can't even tell the difference. All right, and then it looks like it's a 1/2, doesn't it? Now let's try on the other side. So negative 0.01, negative 0.001, negative 0.0001. So do you see how it's approaching from below here and approaching above from here? So if you take a look at the graph, I didn't follow my own rule. I always like to hit zoom standard first because then you have to sit and wait. And usually standard window is at least a good place to start. Well, it's hard to see, but let's zoom in. Zoom in right here at 0, 0. Let's see if that's a better picture. So there it is. So you can see it's coming in. There's going to be a hole here. So if I try to evaluate exactly at 0, so calculate the value at 0, you can see it doesn't give you anything because it doesn't know the answer because there's nothing there. And if I actually put in a 0 here, I should get an error because there's a little point, there's a hole there, but everywhere close to there, right, is going to be close to that 1/2. Okay, so there you have it. I guess we'll do a couple of other ones on another video. We'll break them up into pieces. I hadn't planned to, but we will. We'll break them up into pieces so that you don't have to sit too long if you want to go back and just watch one type or another. So this video we did direct substitution, and I'm going to call this one rationalizing, because that's what we basically did. We used the same steps as we would if we were rationalizing. But remember, what are we always just trying to do? We're always trying to get it so we can do direct substitution. And if we can't do direct substitution, then that means that we have to find some other method, or the limit does not exist.